Good afternoon, everyone. So today we start with a new lecture topic on wireless networks. The last few weeks we were looking at issues related to wire networks, particularly towards the end we looked at Ethernet based local area networks, then the Ethernet switched, or for example extended LAN, which is based on Ethernet switches or bridges. Okay. So today we look at wireless links, particularly we look at 802.11 Wi-Fi, okay, and also we look at the underlying uh, collision issues or protocols and other things and some standards, okay. And we all know that wireless links transmit electromagnetic signals, okay. There are different modes of communications by radio, microwaves or infrared waves. Okay. Wireless, when compared to uh, the wired one, okay, this shares the same wire or medium, but here the medium is uh, the space. Okay. Then the question here or the challenge is that how efficiently we are going to share the wireless medium. Okay. It's basically a broadcast medium. Okay. And in other words, the sharing could be accomplished by means or along the dimension of what is called frequency and the space. Okay. So either it could be by the geographically different locations, okay, or it could be on different frequencies or sequence of frequencies, so which would help us to share the medium. Okay. Particularly, we are interested to share the medium without interference because the wireless medium is broadcast medium. So usually what's happening is that in a particular country or geographical area, okay, the frequency or particular frequency bands, okay, are allocated to specific purposes mostly by the government. Okay. For example, the government may reserve certain frequency bands for, let's say, TV purposes, TV broadcast purposes, or radio purposes like FM radio. We need to reserve, the government will reserve some frequency bands. Some frequency bands could be reserved for military or government use. Okay. So that's all governed by usually the government. Okay. The spectrum allocation or the frequency bands. Okay. And some frequency bands, okay, allocated to maybe different organizations or telcos and other things, and some, okay, are license exempt. That is, some frequency bands, okay, do not need specific licenses. Okay, they are exempted from license. For example, you take our cordless phone, or take for example Wi-Fi at home, then cordless phone. Okay, so in those cases the communication is wireless medium, but okay, there's no specific license is required to use certain frequencies. Okay, okay. So but the next question or challenge is that, okay, because the license is exempted for certain frequencies, okay, we need to impose certain restrictions. Okay. For example, you take cordless phone, okay, in our home, okay, so its reach is limited. Okay, so you cannot use the cordless phone for a very long distance. Okay. Why is it so? Because there are other issues, because there are many users who are using cordless phone or Wi-Fi in the same region. Okay, there are some limitations or restrictions imposed. Okay. The first one is to limit the transmission power. Okay. Okay. So for cordless phone or the Wi-Fi based communication, the transmission power is limited, so it cannot go beyond certain feet or meters. Okay, this is because there are many users who are trying to use. Okay, it's one good reason. Okay, so we don't want to reach for a long distance. Could be more possibility of interfering with others and other things. Okay, and also uh, they will impose what is called the use of spread spectrum technique. Again, this is to reduce, okay, or avoid interference of signals between different transmissions. Okay. So what is this spread spectrum technique? We are not going into the details of the physical layer techniques, but we look at some examples, okay, some the concept or the key idea, okay, those techniques. Okay. So when we say spread, the spread spectrum means that it spread the signal over a wider frequency band. Okay. So the purpose here is to reduce or minimize the impact of interference from the devices among each other. Okay, because the transmissions, okay, when the signals are transmitted in the wireless medium, there's a possibility of interference that need to be minimized. Okay, initially, okay, such wireless transmissions or wireless network or whatever it is was used only for military use. Initially means now several years ago. Okay, because when I was student or even before I took up job, okay, so there were no cellular phones, mobile phones and other things, okay, but it was limited to only military communication or police communication, okay, for the wireless part. But these kind of techniques like frequency hopping or direct sequence, which come under spread spectrum, okay, are used in today's wireless communications also. Okay. Let's look at the key principle of what is called frequency hopping or direct sequence techniques. What is frequency hopping? The name says, okay, it hops through a sequence of frequencies. Okay, that is, we transmit a signal over a sequence of frequencies, not at the same frequency always, but it goes through, okay, frequency 1, frequency 2, 3, 4, 5. Okay, it hops through different frequencies, and the sequence of frequency is random. Okay, it randomly picks up the sequence. Okay, it's actually pseudo random, it's not random, so we call it as truly random. You take any random number generation, it depends on some initial seed value. Okay, although it's random, for that seed value, okay, it will go through some particular order. Okay, so the sender and the receiver, okay, both agree on this kind of random sequence. Okay, and they sync to each other, they use the same algorithm. Okay, so they will be able to recognize, okay, the signals, what is sent and other things. So this is called frequency hopping. Okay. The second technique which is used is the direct sequence technique. Okay. So this is also quite simple, easy to understand. That's the basic concept. So in this case, each bit is represented by a sequence of bits in the transmitted signal. That means for each bit to be transmitted, let's say you want to transmit 1, or let's say you want to transmit 0. So instead of 1, we are going to transmit a sequence of bits. Instead of 0, we transmit another sequence of bits. So what is the sequence of bits which need to be transmitted? That depends, that is based on a random sequence. Okay, that depends on a random sequence. Okay. A sequence of random bits is generated by a random number generator, because usually random number generator is a pseudo random number generator, because for the given seed input, okay, the randomness is defined kind of thing. But this is known only between the sender and receiver. Okay. And the transmitted signals, that's a sequence of bits. Okay, each sequence corresponds to one particular bit, the actual original bit. Okay, so called n-bit chipping code. Okay. It spreads across a frequency band n times wider. I mean, to understand, or to put in simpler term, to transmit one bit, we are going to transmit n bits, n number of bits. So instead of transmitting one bit, we transmit a sequence of 4 bits. So this, we say that the frequency band is 4 times wider. Okay, so this is how it's going to be. Maybe we look at an example, then the technique should be clear. Let's say we are interested to transmit a data stream 1010. 1010. Okay. It's not transmitted as 1010, but to transmit 1, we are going to transmit a sequence. To transmit 0, we transmit another sequence. But which sequence we generate, it depends on a random sequence which is agreed by both sender and receiver. Let's say the random sequence is this, which is known to the sender and the receiver. Let's say both use what is called 4-bit chipping sequence. That means every bit is replaced by a 4-bit number. Every bit is replaced by a 4-bit number. Okay? So you take the first 4-bit, 0, 1, 0, 0. Okay? And here first bit is 1. You stretch 1 4 times. This is 1, 1, 1, 1. So this corresponds to the first one. Okay? The second bit is 0. This is stretched into 4 bits, 0, 0, 0, 0. Then third one, this one is 1, 1, 1, 1. And the last one is 0, 0, 0, 0, 0. Is that fine? Now, this is the random sequence 0, 1, 0, 0, 1, 0, 1, 1. So 0, 1, 0, 0. Then 1, 0, 1, 1, 1, 0, 1, 1. Okay. So this is how the given random sequence is. That means this random sequence will cycle through. That means will repeat. This is a 16-bit random number. Okay. So what is the actual transmitted signal? To transmit 1, this will be exclusive OR with the first 4 bits. Okay. Exclusive OR operation. The first 4 bit is 0, 1, 0, 0. So 0, 1, 0, 0. This 1 is 1, 1, 1, 1. So this is 1, 1, 1, 1, 0, 1, 0, 0. So you take exclusive OR 1, 1, 0, 1. So the sequence which is sent is 1, 0, 1, 1. So this is 1, 0, 1, 1. Is that fine? And the second bit to be transmitted is 0. So stretch it to 4 bits, 0, 0, 0, 0. So 0, 0, 0, 0. And the next 4 bits in the random sequence is 1, 0, 1, 1, 1, 0, 1, 1. Okay. So this 1, 0, 1, 1 is this 1, 0, 1, 1. So take exclusive OR, corresponding bits are exclusive OR. This becomes 1, 1, 0, 1. So you can see the transmitted bit is 1. Sorry, this is 1, 0, 1, 1. Is that fine? So this is how every bit is transmitted. So if it's a 8-bit sequence, 8-bit chipping sequence, then 1 bit will be transmitted as 8 bits according to the random sequence which is agreed by both sender and receiver. So this kind of randomness or spreading the frequency, okay, helps to reduce the interference. Any doubt? So this is not encryption. Okay. This is a kind of coding kind of thing. Okay. Because this random sequence, okay, is agreed by only the sender and receiver. Okay. In the previous method, frequency hopping, there is a randomness, but here it goes through a random sequence of frequencies. Frequency 1, frequency 2, frequency 3. Okay, in some random sequence, these frequencies, the signals are transmitted in different frequencies. Okay, so different pairs of communications could take place. Okay, but because it goes through a sequence of frequencies, so the interference is low or minimized. So when we say wireless technology, okay, there are two key parameters which specify this. One is the bandwidth. The other one, bandwidth here is the data rate. Okay. So the other one is how far apart the communication nodes be. That means what is the communication range? What is the communication range. Let's say node A wants to communicate to B. If I use this wireless technology, how far I can reach. Okay, it's not that I can reach maybe another node after 1 kilometer, 2 kilometers. We cannot, right? So you see, for example, use Wi-Fi, you can reach maybe a few feet. Bluetooth, maybe less than that. Okay, so let's quickly look at some key wireless technologies. Bluetooth, the standard is 802.15.1. Okay, and the typical data rate is bit low. That's around 2 Mbps, 2 Mbps, and the communication range or reach is up to 10 meters. Up to 10 meters. We know, I mean, Bluetooth usually maybe for wireless set to phone communication, very short distance communication only we use. Even though it is 10 meters, maybe depending on the room or materials and other conditions, maybe less than 10 meters. Maybe in an open space without any obstacles, in ideal condition could be up to 10 meters. Then Wi-Fi, there are different 802.11 standards, okay, B, G, N, AAC, those kind of Wi-Fi standards. So they all differ in their data rates as well as the range, okay. But we can transmit up to, let's say, a few hundreds of Mbps with the latest ones like AC and other things. Also, there are claims on achieving even few Gbps transmissions, and the range could be up to few tens or maybe let's say 100 meters in the ideal condition. Okay. And if you look at, okay, the cellular communication, 3G or 4G, the communication range could be more, could be tens of kilometers. That is our device when you connect to the network, okay, by 3G or 4G, the tower to which we are associating our device could be within tens of kilometers, not like Wi-Fi. If you take Wi-Fi, okay, we attach our device to the closest Wi-Fi access point. That will be few meters, okay, right? But for 3G or 4G, it could be few kilometers. And the data rate could be even hundreds of Mbps. Maybe with 5G and other things, they talk about even the order of higher capacity like Gbps and all. This is just for your information. We should be aware that different wireless technologies exist. Okay, and the popular connectivity or in practice how wireless network is used, okay, is by means of the asymmetric infrastructure. Okay, it's an infrastructure mode communication. It's asymmetric in the sense that, okay, usually what we have is we have the hosts, maybe phones or computers. They don't communicate directly. They do not communicate directly, but usually communicate through some wireless access point or base station, okay, which is connected at the background to the wire network. Okay. That means there are some entities which are mobile. So these are the mobile devices, laptop, okay, or our phone, which can move around here and there, okay. But there are some devices, this part, which are not usually mobile. We fix the wireless access point somewhere, okay, and this maybe in the campus also wireless access points are there here and there. Then wireless access points are connected in the backhaul by a wired network. Okay, the wireless connectivity is between our device to the access point. Behind that, there's a wired network which is used to connect to the internet. Okay. Now, depending on the mobility of the nodes, okay, so there are different wireless technologies, okay, which support different levels of mobility. Okay, for example, in some cases there should not be any mobility. Okay, that means the sender and receiver both are fixed. maybe you say on top of the buildings, two buildings, okay, we fix some transmitter and receiver, they communicate directly, okay. So they fixed transmitter receivers, okay. WiMAX, okay, is a good example for this, but I don't think WiMAX is quite popular now, okay. But if you take Bluetooth, mobility of the users is allowed, but within the range of the base, okay, within a small range, we can move here and there. Is that fine? Let's say you connect to your phone, your wireless headset connect to the phone, so you can move here and there, okay, nothing wrong. But if you take Wi-Fi, this is a bit different. Similarly, the cellular network, 3G or 4G, here even we can move between the base stations, between the access points, okay. Let's say you are connected to Wi-Fi, you can move here, you may be attached to one wireless access point, okay, and you can continue to move, you may be attached to another wireless access point, okay. So that means the mobility is possible between different base stations or access points. Similarly, cellular tower. Let's say you are traveling in the bus, okay, you are connected to maybe some cellular tower. Now you get 4G service, but travel, okay, further, you may be attached to another tower. You may not be knowing it, okay. So that means the mobility is permitted between the access points. That's not possible for Bluetooth. You cannot move from one Bluetooth to another Bluetooth. But within the same region, you can move. Okay. Wireless communication supports another kind of network structure, which we call it as mesh network. Wireless mesh network or ad hoc network. Okay. In ad hoc networks, all our peers are at the same level. Here, they are not peers because this has different capability, this has different capability, okay. This could be mobile, this is not usually mobile, this is connected at the back here, they have different functions, they cannot communicate directly, it's not possible, but they can communicate here, then communicate here, this is possible, am I correct? But in the case of wireless mesh, okay, two nodes, they can communicate directly. Two wireless devices can communicate directly, or if the other device, that is the destination, is not within the range, it can go through multiple hops. For example, this node, let's say A, B, C, A and B can directly communicate, B and C can directly communicate. If A wants to communicate to C, it can communicate through B, then C. So every node is treated as equal, peer, okay. So it can communicate directly or it can act as a relay. So here B relays A's packet to C. Similarly, A can relay, let's say some other nodes, let's say this packet, this frame to this. Okay. So we say that messages are forwarded via one or more pair nodes, via a chain of pair nodes. So this kind of network is called ad hoc networks or wireless mesh networks. Any doubt? Okay, now let's look at the Wi-Fi. Okay. Any idea what does it stand for? Wi-Fi? Yes? Wireless fidelity? Yes? Then any other reason why it's called Wi-Fi? Maybe you look at literature and books. Okay. Huh? No. Okay. It's not clear why it's called Wi-Fi. Is wireless fidelity or some other is all like hi-fi. People want to call as Wi-Fi. Okay. But let's not worry about it. Okay. Why it is called Wi-Fi. Okay. So let's look at the underlying protocol, how to deal with collisions, whether collision can happen, can we avoid collisions, this, that, all those things. Okay. So Wi-Fi is meant for maybe it's a local access network or local area network. Okay, it's a kind of LAN, wireless LAN, local area network. Maybe you can also call it as access network because this connects our device. Okay, to this helps to connect our device to the internet. Okay, this is just to provide the internet access. So from that perspective, it's an access device. Is used within the home or offices or small rooms, campus, etc. Okay. But because it's a wireless communication and it's also a shared medium communication, okay, the challenge is the MAC. MAC is the challenge. Medium access control is a challenge. Okay, so how we make sure that there is no collision, okay, or can we avoid collision, okay, if at all there is a collision, okay, how to deal with that, is there a possibility of collision first of all, okay, so how we can approach this, etc. Okay. It also does other features. We are not looking into the power and security features. Mostly we look at the medium sharing, okay. Okay, so this slide lists maybe the history of Wi-Fi, different standards, okay, how it evolved, okay. The original 802.11, okay, started with uh, the basic two techniques, the frequency hopping technique. Just to recall, it hops through a sequence of random frequencies, okay. It uses 79 1 megahertz frequency bands, okay. And the other possible technique which can be used is the direct sequence, okay. Usually 11-bit chipping sequence is used. In the example, for simplicity, we looked at 4-bit chipping sequence. Actually, 11-bit chipping sequence was used. Both run on 2.4 gigahertz, and the bandwidth initially provided was 2 Mbps. Okay. This is the initial 802.11. Okay. And it evolved through different standards. Okay. As you know, nowadays we have 802. Wi-Fi, which work on two bands, 2.54 as well as 5 gigahertz. Am I right? Some of our phones are mostly routers nowadays. They support dual band, the two bands, 2.4, 5 gigahertz. Similarly, your devices also, at least high-end mobile devices, it supports both 2.4 and 5 gigahertz. Am I right? So when you go home or here, okay, we can attach to 2.4 or 5 gigahertz if it supports both. Okay. Okay. The first, then the physical, okay, starting from 802.11, the next standard which evolved was 802.11b. Okay. Though you don't need to memorize all those things, but better you know, okay, the evolution, okay, how it went through different standards. It uses a variant of direct sequence technique, but the data rate is increased to 11 Mbps in the case of 802.11b. Okay. Now also you'll see something like BGN. Do you remember AC 802.11? So if you look at the specifications, usually you see BGN. It's compatible with BGN. Okay. So B is up to 11 Mbps. Okay. Of course, it uses license exempt frequencies. Okay. Wi-Fi operates on the not the licensed spectrum, but license exempt spectrum. Okay. 2.4 gigahertz band. Then came A. I don't know. First came B, then A. Okay. So it could provide up to 54 Mbps, but it uses orthogonal FDM technique. Okay. But it runs on 5 gigahertz band. It's not that popular now. We usually see BGN. Okay. Then came G, 802.11G. Okay, it's backward compatible with B. It uses 2.4 and the data rate up to 54 Mbps. Then evolved what is called 802.11N. Okay, that improves on G. Okay, it works or it operates in 2.4 gigahertz band. It could offer few hundreds of Mbps. And interestingly, it uses MIMO, multiple input, multiple output technique. Of course, we are not going into all those physical AI techniques, but you just remember that, okay, it's possible to use different kinds of techniques, okay. And similarly, the recent one, 802.11 AC, it improves on N, 11N. It operates in 5 gigahertz band. It's able to offer up to few gigabits per second data rate. It also uses MIMO technique, multiple input, multiple output technique. Okay, this is how they have been evolving. Okay, now we are ready for the so-called MAC, multiple access. Okay. We say it uses 802.11 uses CSMA CA. If you can recall, Ethernet uses CSMA CD. Okay, CS stands for carrier sense, MA stands for multiple access. Multiple access we don't need to explain much. Okay, CS stands for carrier sense. Carrier sense means, okay, any device, okay, before it starts its transmission, it senses the medium. If it already can see or hear that some transmission is already going on, then it will not transmit. Because if it transmits, obviously there will be collisions, right? So this is carrier sense. But it does not have collision detection capability. There is no feature, collision detection feature. There is no collision detection, but it uses what is called collision avoidance. Collision avoidance. Okay, first let's see why there is no collision detection. No collision detection. There are few reasons. Okay, you take a wired network like Ethernet, the signals propagate through the wired medium, and the fading of signal, okay, is not a major issue. Okay, so when the signal starts from here and reaches the other side, okay, if sufficient bits are sent, okay, sufficient energy you will get there to detect collision. Okay, but in the case of wireless medium, the received signals are weak. Okay, and it travels us more and more. Okay, due to fading, okay, the signals become weak. Then at the receiving side, it's very difficult to sense the collision. Okay, so 802.11 prefers not to have this kind of collision detection mechanism. Okay, similarly, we also look at later with examples that in some cases not possible to detect collision in the case of wireless communication, mainly because of the communication reach, how far the transmission can reach. Okay, if the communication can reach 10 feet, then it can reach 10 feet this side, 10 feet this side, 10 feet this side, like a circle. You cannot reach beyond that. Okay, so because of the communication reach, okay, as we see slightly later, this has what is called hidden node problem, okay, which also makes us think twice, okay, why should have collision detection mechanism. Instead, it has collision avoidance. It's a very interesting one. Okay, later we see how it avoids collision. Okay, so somehow it can predict or sense that, okay, if it transmits now, it will lead to collision. Okay, so it tries to avoid collision by the protocol. Okay, so obviously when you try to avoid, then some kind of coordination, some kind exchange of some messages required, okay, before it starts transmission. Okay, first let's look at the two interesting problems in which are specific to this wireless communication: hidden node problem and exposed node problem. I tried to explain with an example. Okay, this is taken from Peterson Davy. Of course, you can see similar examples in other books as well. Okay. Now look at this case. See, there are three nodes or three hosts, A, B, and C. And this circle, let's say blue color circle, is for, this is for A's reach, or basically A's communication range. Okay. So whatever is transmitted by A, okay, will be received by any host within this circle, within this blue color circle, because that is the reach of A. Is that okay? Similarly, the other circle, this shows the reach of C. We don't show here the circle for B, okay, because for this example it's not required. Okay. So what does it mean here? A, whatever A transmits, B can receive. Okay. Maybe you look at from B point of view. Whatever B sends, okay, B, whatever B transmits, A can receive, C can receive. Is that fine? But you take C. C can reach B because it's within the C circle. But C cannot reach A. C cannot reach A. That means whatever is transmitted by C cannot reach A, but it can reach B. Similarly, you take A can reach B because B is within its own circle, okay, within its reach, communication reach. But A cannot reach C. A cannot reach C. Now, for this particular scenario, let's see what happens. Let's say A and C both want to communicate with B. Okay, so A communicates with B and C also wants to communicate with B. Okay, so what happens? A communicates with B, so whatever A is transmitted will be received by B. Okay, but the A's transmission will not be received by C. We say C is hidden from A. C is hidden from A. Similarly, when A transmits, when C transmits, the signal will be received by B, but C's signal or transmission will not be received by A because C and A are hidden with respect to each other. They cannot directly see, they cannot directly communicate. So what happens? B receives from C as well as C simultaneously, and there is a collision at B. There is a collision at B. Collision with what? That means A's frame, which was sent to B, collided with C's frame, which was sent by C to B. But A does not know that its own frame has collided. Similarly, C does not know that its frame has collided. It had a collision at B. Why? Because C's transmission cannot reach A. So A has no clue, or A cannot detect collision. A's transmission cannot reach C. So C cannot detect any collision. Is that fine? Okay. Now let's look at the other kind of problem, that is exposed node problem. It's also, this kind of problem occurs in wireless communication. Okay, but to be frank, it's not a problem. Okay, it's an advantage actually. Okay, so what is this? Again, look at this example, A, B, C, D. So we the blue color one is the B's circle, that is B's, which shows B's communication range, and the other circle is for C. Other circle is for C. Okay, we will look at this. So we say that B and C are exposed to each other. B and C are exposed to each other. That means whatever is sent by B will be received by C. Whatever is sent by C can be received by B because both are within the same circle. But you look at A and D, okay, they are hidden from each other. They are not in the same communication reach. Okay. Now, let's say B transmits to A. B transmits to A. Okay. So, C receives. C can also hear the communication. Am I correct? B, okay, transmits a frame to A. It's a broadcast. Okay. So, A receives, but C also receives that. Is that fine? But so that means C senses that some communication is going on. Okay. So now what C will do? Okay. So that means C should not transmit. Am I right? C should not transmit. Need not be. In some cases, C can transmit. Okay. For example, C wants to transmit to D. Let's say C wants to transmit to D. So C wants to transmit to D. Okay. Then D is receiving this signal. Here A is receiving the signal from B. Here D is receiving the signal from C. So there's no interference between the two transmissions, B to A and C to D. There are no interference. That means when B transmits to A, C can hear that. That doesn't mean that C should not transmit to D. In this particular case, C can transmit to D, okay, because D and A, they are far apart. They don't interfere. Okay? Is that okay? So it's possible in some cases, even though C can hear the communication, it can sense that there is some transmission ongoing, but it's permitted to transmit to D. So we are going to look at the protocol, okay, which helps us to see, oh, okay, can C transmit to D or not? Okay. Is it clear? The expose node problem, as I said, rather than it's a problem, it's an advantage. Okay. We can leverage on that to have multiple transmissions like B to A and C to D. Okay, let's look at 802.11 collision avoidance protocol. Okay, so we call this as MECA, multiple access with collision avoidance. Multiple access with collision avoidance. Okay, because it's avoidance, some level of coordination is required. Okay, because somehow they need to agree to have a transmission or not to have a transmission. Okay. So what sender and receiver do is this. Initially, the sender and receiver, they exchange some frames. We call them as control frames because they are not data frames. They are control frames, okay, to make a decision, okay, whether they can proceed to transmit or not. This is something like, okay, hello, okay, I want to send something to you. Okay, are you ready to receive? Then the other fellow may say, okay, I'm ready to receive, you can send it. Okay. So if such handshaking, it's a kind of handshaking, okay, is completed, then they are free to transmit. Okay. So what is done is this. Sender transmits a control frame called RTS frame. RTS stands for request to send to the receiver. Actually, it's a broadcast. Okay, though we say it sends or transmits, it's received by many in the reach. Okay. RTS frame, okay, later we also see, it also includes a field in the header, okay, specify how long it wants to transmit. Okay, basically could be translated to what's the length of the data frame to be transmitted. Okay, let's say I want to transmit for 10 microseconds. I want to transmit this many bytes. Okay, is that okay? So that information will also be in the header. This is request to send. What the receiver will do? The receiver will reply. Okay, if it's ready to receive. Okay, if it's already receiving some other transmissions, obviously it will not send a reply. Okay, so it will reply with CTS frame. It's called clear to send. You are given a green signal. Okay, you can send it. So this frame also carries the length field, okay, which was mentioned there. Okay, it indicated that want to transmit 10 microseconds, then it will also echo it. It will say yes, you can transmit for 10 microseconds, no problem. Okay. Okay, now we see, okay, how the two situations like exposed node problem and the hidden node problem, okay, they are handled here, and also how they avoid the collisions, etc. Okay. Now, very simple, any node which can see CTS frame knows that it is close to the receiver. Okay. Let's say this is X, this is Y. Let's say X sends an RTS frame, request to send. Let's say Y is free. Okay, Y sees that it's not receiving anything, so it's ready to receive the communication. So it will respond with CTS. Okay, it's a broadcast. If the same CTS is received by Z, let's say Z is within the reach of Y, okay, then Z will receive CTS. Am I correct? So if Z can see CTS, it will understand that there is somebody close to him, let's say Y, okay, who is going to receive some data. Okay, so that means Z and Y, they are within the communication range, within the communication reach. Is that fine? So if it can see CTS, Z will not send. It will not send any new frame. Okay? So any node that sees CTS frame knows that it's close to the receiver. It's close to the receiver, so it cannot transmit. How long cannot transmit? It transmits for the time period which it has seen in the CTS frame, because CTS frame will tell, okay, 10 microseconds, okay, or how many bytes, okay, the transmission has. So during that period of time, it will not try to transmit anything. Is that fine? Because if Z also starts its transmission, then it will collide with Y. Now, there is another scenario. A node sees RTS frame, but it does not see the CTS frame. A node sees RTS frame, but does not see the CTS frame. Now look at the exposed node problem, A, B, C, D. Okay, A sends let's say B sends RTS frame. B sends RTS frame. Let's say B wants to send some frame to A. So C also receives the same RTS frame, because B and C are within the range. This is something like this. B sends an RTS frame to A, so the same RTS frame will be received by C also. Okay. Now, this communication is meant between B and A, so A will respond with CTS. A responds with CTS. Okay. But when okay, whatever B sends will be received by both. But whatever A sends, it will be received by this. Maybe this. Maybe A circle should be something like this. Okay. So whatever A replies will not be received by C. That means this CTS cannot reach C. Okay. That means C receives RTS frame, but subsequently it does not receive the CTS frame. That means what? The receiver A is far apart from C. Okay? The transmission is towards a node, let's say A, which is far away from C. This implies that C can have its own transmission. That means C can transmit to this RTS, then this can respond with CTS. Okay. So the rule is this: if a node can see RTS but not CTS, it's not close enough to the receiver for the interference to happen, so it's free to transmit. Okay. Any doubt? CTS collides with what? No, which node? No, which one? D. Here. Oh, this one. Yes. Yes. It's already transmitting. No, if it's already transmitting, okay, then that transmission can be heard by Y. Am I right? Then Y will not respond with CTS to X. Is that clear? Yeah, both ways. Yes. Any doubt? Okay, there is another variant of MECA which we call it as MECA W, that is MECA, okay, multiple access collision avoidance, okay, for wireless LAN, okay, which includes an acknowledgement, okay. That means the receiver sends an acknowledgement to the sender after receiving the frame, data frame. So first the sender sends RTS, receiver sends CTS, then the sender sends an sender sends a data frame, okay, and the receiver will send an acknowledgement, okay, and this acknowledgement also helpful. That means all the nodes which were seeing that some transmission is going on, okay, they will wait for the acknowledgement, in the sense that, okay, the receiver has already acknowledged the frame, then they will decide to send their own RTS frames, okay. But here still there is a small possibility of collision. That collision can happen between two RTS. Okay, two nodes may at the same time, okay, find that, okay, nothing is, there's no transmission going on. Let's say X, or maybe let's say A, B, and C. Okay, let's say no transmission is going on. So A may send RTS, and C also may transmit RTS. C also may transmit RTS. Okay, that is request to send, is a control frame. So in that case, there's a possibility that both may be received by this node. So there's a collision. Okay. So if B is the receiver for both, let's say A wants to send to B, is the intended destination. C also wants to send to B. Okay. So here RTS have experienced collision. Okay. There's no explicit collision detection mechanism. Okay. But if there's a collision, the receiver will not send the CTS back. That means if the CTS frame is not received after a period of time, okay, because it doesn't, okay, a node has sent RTS but it's not receiving CTS, then it understands that something has gone wrong with the RTS frame. Okay. So it will wait for a random amount of time before transmitting RTS again. This is similar to the Ethernet's backoff, exponential backoff algorithm. Do you remember? First time it, it, it backs off, okay, for 0 or 1. Second time 0, 1, 2 or 3, okay. So random period of time. So that kind of backoff is used only for RTS purpose, not for data frame. Because once RTS, CTS pair they decide handshaking is over, that means they are free to transmit and receive. There should not be any collision. Any doubt so far? Yes? Okay. Now, we will look at what is called infrastructure based communication between two wireless nodes. Okay. As we have seen before, okay, there are two possible modes. One is ad hoc in the sense that everybody is free to move and they can also uh, directly communicate to others. If they are within the range, they can also communicate to others through more than one hop, like A can communicate to C through two hops. Okay, so this kind of mobility, ad hoc mobility and peer-to-peer communication kind of things is the ad hoc mode of working. But what is practically used now, maybe in home and the offices, okay, is basically infrastructure based communication. So infrastructure based communication is something like this. We have different access points. AP stands for access point. Okay. That means you can see here A, C, B, there are some nodes. Okay. And there is an access point AP1, AP2, AP3. Maybe this is something like in an organization you have different wireless access points. As I said before, your device may be connected to this wireless access point. Maybe when you move further closer to another access point, you may be attached to another access point. Okay, similar to the cellular towers. Okay, you may be attached to different towers when you are mobile from one place to another place. Okay, so in this case, it's a kind of seamless communication kind of things. Okay, it's called infrastructure mode communication because you don't directly communicate like peer-to-peer communication. You communicate to an access point. Okay, then from the access point, the frame is forwarded to another host, or at the back end, all these access points, they are usually connected by a network. This is another network. It's network, usually they have Ethernet switches or routers. Okay, so at the back end, these access points are connected by a network. Even the cellular tower also, they are connected in the background by routers. Maybe locally in the company, these wireless access points may be connected by Ethernet switches. Finally, because that helps to connect to internet and other things. Okay, is that clear? So this is called distributed system because this is all geographically distributed. Okay, few hosts A, B, C, they are attached to access point 1, then B, D, H attached to access point 2, then let's say F, E and G to access point 3. Is that okay? Now, if A wants to communicate to C, okay, both are within the same region, okay, under AP1. So A can communicate to AP1, which can send the frame to C. Okay. On the other hand, if A wants to communicate to D, then A can send it to AP1. Then through the distributed system, it will be connected to AP2. Then this is connected to D. Okay. So how A and D communicate, A to AP1, access point 1, access point to access point 2. The communication is from the backend network. Similarly, A can communicate to E. So A can send its frame to AP1. AP1 will forward it to AP3 through maybe a sequence of switches. Then finally from AP3, the frame will be forwarded to E. This is how it works. Okay. So we say that every node or each host associates itself with one access point at any time. So A is attached to AP1. C is attached to AP1. But B is common to both circles. It can be attached to either AP1 or AP2. Later we see that by scanning method, it might prefer AP1 over AP2 or it may prefer AP2 over AP1. So it will choose one between these two. Is that fine? Okay. So maybe look at this case. C is initially associated itself with access point 1. Maybe in the case of Wi-Fi or wireless is a small box. In the case of cellular communication, it's a cellular tower. Okay. So let's look at Wi-Fi. So it's an access point. Okay. This is something like a base station. Okay. So C is attached to access point 1. Let's say C is mobile. C is moving. C is moving. It's not inside the room, but started moving. So slowly, after this point, it will receive signal from AP1 and AP2. So it has a choice now. It can be attached to AP1 or AP2. So there's a mechanism by which it can choose. Maybe depending on the signal strength, it may find that AP1 is better. It's moving closer to AP1 or away from, it's moving away from AP1 and moving closer to AP2. So during this time, okay, this will associate itself with AP2. Okay. How it is done? Very simple mechanism. Okay. So the technique which is used to associate a particular host to a nearby access point is called scanning. Okay. Basically, a host is attached or associated with an AP. So procedure is called scanning. Okay. Very simple. The node or host sends a probe frame. Okay. It sends a probe frame. It could be sent periodically. Okay. There's a control frame. Okay. And any access point, there can be more than one access point which can receive the probe. Okay. Will respond with probe response. Maybe access point 1 may say, okay, yes, I can serve you. Access point 2 also can say, I can also serve you. Okay. Then the node selects, okay, I don't want access point 1. Let's say I prefer access point 2. Then it sends another control frame called association request to the one which it has selected. Okay. So then that particular access point will respond with what is called association response. Now everything is done. Now it has moved from, or it has shifted its association with access point 1 to access point 2. Okay. So when it will switch over to a new access point, or when it will engage this, of course, whenever it joins the network, let's say first time it's trying to join, obviously it has to send the probe signal to find what's the nearby access points. You can also see there are many access points you can see from your device. Am I right? Of course, there are some security features. It may not allow you to attach to more than one. Some are locked. Some security features are there. If it is not secure, so you are free to attach. Usually the one with the highest strength, okay, would be chosen. Okay. So if the signal from the current access point is weak compared to maybe another access point, it may be attached to another access point. Whenever a node is attached to a new access point, it will notify, the new access point will notify the old access point of the change via the distribution system. Okay. That means initially it is attached to this, then later to this. So once it is attached to this, this AP2 will inform AP1 that C is no longer with you. So this kind of scanning is called active scanning because it is the node or host which is actively searching for an access point. So in this case C, when it starts moving here, here, okay, so at this point, as I said before, the probe signal will be received by both AP1 and AP2. Both will respond. If it moves further, okay, it will choose AP2 instead of AP1. Again, it's called active scanning because it is the host who actively engages, who actively searches, okay, for a good access point. On the other hand, it's also possible, it supports the other kind of scanning, which is called passive scanning. In passive scanning, the access points periodically sends beacon frame. Okay. So in that case, the host does not probe, but instead the access points periodically sends out the frames, beacon frames. They advertise, okay, hello, this is, I am access point 2, I am access point 1. Okay, this is my capability. Let's say this is the transmission rate I can support. Okay, some information it gives. Okay, then based on this, the host will respond. Or if it wants to associate, it will respond with association request. Then the access point will respond with association response. Okay, maybe let's look at the same thing, maybe a different example from the other book. As I said before, whether you refer book 1 or book 2, okay, the concept is same. Only the example they put maybe in a slightly different way. So let's see how Croce, the author Croce, this book, okay, presents it. Now look at this case of passive scanning. Look at this. This is an access point, wireless access point. This is the host. This is another access point. And you can see that this host, okay, is within the reach of both AP1 and AP2. So it's at the intersection of the circle. So it can associate either with AP1 or with AP2. It has a choice. In the case of passive scanning, every access point will periodically broadcast beacon frames. So this is number 1. This is step 1. So host 1 receives both beacon frames, and let's say it decides to prefer, it prefers AP2. Then it sends number 2, step number 2, association request message to host 1, to AP2. Then AP2 will accept it. It will respond in step 3 with association response. Okay. So host will say, hi AP2, I want to associate myself with you. Can you serve me? Then AP2 will send, okay, you can be attached to me. I can do service for you. I can serve you. I can forward the frame to you. I can forward your frames to others. Okay. This is how it works. It's called passive scanning. Now look at this. This is example of active scanning. So in this case, as I said before, the host should be proactive. It should initiate. This is active scanning. Who initiates it? Host initiates it. This host in step number 1, it sends probe request. You can see 1. In step 1, sends probe request to AP1 and AP2. Basically, it's a broadcast. So AP1, AP2 both will receive in this case. Okay. Then both will respond. In number 2, AP1 responds, AP2 also responds. Then host 1 chooses. It decides its preference, who it prefers. Okay. Let's say host 1 prefers AP2. Then it sends in step 3 association request. In step number 4, AP2 will respond with association response. Now everything is done. Okay. Any doubt? So this is happening in distributed system where more than one access points are there. Okay, and these access points are connected by a network of switches or routers in the back end to connect to the internet. Any doubt? Okay, let's move on to the frame format. Okay, the last 32 bits is CRC bits used for error detection. So usually every link layer protocol has CRC to detect errors. Okay, and look at this payload. It supports 2312 bytes. Also don't know how these numbers, how they arrived at this number. Okay, Ethernet 1500, easy to remember. Okay, but here the data can be up to 2312. Okay, then the initial 16 bits, which we call it as control field. Okay, and this control field, it tells whether the particular frame is a data frame, or it's an RTS frame, CTS frame, or it's a part of scanning like probe request, probe response, okay, association request or association response. So some bits here will indicate the type, whether it's data, RTS, CTS, or it's a scanning control frames. Okay, and there are other bits also. They are of not interest to us. There are also 2 bits, a pair of 2 bits. Okay, the 2 bits are called to distributed system and from distributed system. To distributed system and from distributed system. Okay, so why do we need this? I will explain it slightly later. Okay, and also there is a field called duration. Okay, as I said before, when a node sends RTS frame, it also specifies the duration, how long it wants to transmit, depending on the frame size in terms of microseconds. Okay, it will tell. Okay, and the sequence control is not of interest for fragmentation and other purposes. But let's look at the address fields. You can see that there are 4 address fields. Address 1, 2, 3, 4. If you look at the Ethernet frame, there are only 2 address fields. The first address is the destination address. The second address is the source address. But here there are 4 address fields. Why we have 4? This is because of the distribution system. For example, A wants to communicate to E. So A has to communicate to AP1, then AP1 to AP3, that's a backend communication. Then AP3 to E, another communication. Am I correct? So within this wireless mode, there are 2 communications, A to AP1, A to AP1, and AP3 to E. So there are 4 people, 4 entities involved here. The original sender is this. Okay, the actual destination is this. But in between, there's an intermediate destination. This is an intermediate destination for this. And this is an intermediate sender for this. This is the actual sender. This is the receiver. There are 2 intermediate nodes which act as the intermediate receiver here, intermediate sender here. So there are 4 people involved. Okay. So to support this, there are 4 address fields. Address 1, 2, 3, and 4. Okay. That's why we say to distributed system and from distributed system. Okay. The simplest case is this. What is the simplest case? One node is sending directly to the other node. one is sending directly to the other node without any AP. That means maybe is a peer-to-peer kind of things. So if both DS bits are 0, two distributed system from distributed system both are 0, that means they are not communicating through distributed systems. So in that case, address 1 is the destination 1, address 2 is the source node. Address 3 and 4 are not relevant, because usually the first address is the destination. Destination address, source address. 3 and 4 have no relevance if both DS bits are 0. Okay. Now, more complex case, let's say both bits, DS bits are set to 1. Two distributed system, and from distributed systems both are 1. Okay. Let's consider the same example. A sends to E. So how A sends to E? A sends to AP1, then AP3 sends to E, and these two are connected in the backend by switches or routers. Okay. So in this case, address 1 is E, the actual target or destination. Address 2 is the sender. This is the intermediate sender, AP3. Address 3 is AP1, that is intermediate receiver. Address 4 is the actual sender. Okay. The actual receiver is E, that is address 1. The next address is AP3. Okay. Then AP1, then A. So all 4 addresses will be relevant when DS bits are set to 1. Okay. Now look at this case. Maybe in a home kind of environment, we have only one access point. Okay. And let's say there are hosts, access point, let's say router. This is router R1 interface. As you know, every interface has IP address and MAC address. Let's say this is Ethernet, and this communication is Wi-Fi. Okay. This is 802.11. This is 802.3. Okay. So there are two kinds of frames. The first frame is Wi-Fi frame between the host and the access point. Okay. But when it goes out to the internet, okay, so this interface is Ethernet interface. Okay. But as far as host is concerned, okay, this host is something like directly connected to the internet through router. Okay. So the format is something like this. For the Wi-Fi part, that is host to the access point, this is the 802.11 frame. How it looks like is this. This is a more practical case. Okay. Address 1 is the access point's MAC address. So this is the destination for this frame. That is, it's sending to the access point. And the sender, the next address is the sender H1 MAC address. But it also specifies R1 MAC address. It also specifies R1 MAC address. Okay. That means this as a whole until this. Why it specifies like this? This information will be useful when access point transmits in Ethernet frame, because this frame is an Ethernet frame, 802.3. Ethernet frame has only two addresses. The first address is the destination address. For this, the destination address is R1 MAC address. The source address is H1 source address. That means as if this H1 is connected to this router like the Ethernet interface, this frame is sent. This is something like a proxy kind of thing. Okay. So how does the access point know? Access point know the R1 MAC address because host 1 specifies here in address 3 field. This field is used as the destination address for this Ethernet frame. For this, the source address is not the access point, but the source address is H1 MAC address. Okay, any doubt? Any doubt? Okay, this is the end of the lecture. We are done with all lectures. On Wednesday, we look at the tutorial 3 problems, and then we have midterm break. After this Saturday, same place we are going to have the test. I understand some of you expressed some difficulties in attending the test. You have other tests in the same time. Okay, maybe it's not a good day. I think it looks like many subjects are conducting. So if you have valid reasons, as I said before, genuine reasons with a proof. Okay, you cannot simply say that I have some other test and all. Okay, some email or some proof. Okay, so you can send it to me. Make-up test will be conducted. Okay, and make-up test is also at the similar difficulty level. Okay, it won't be easier. Okay, is that okay? So yes, 11. So some students, you may want to do more than one test on the same day. In the past also some students did that way. Afternoon they had another test. Morning they had my test. Should not be a problem. Okay, I would suggest you, okay, to try your best to take the test that day itself. Don't try to postpone it unnecessarily. Okay, is that fine? It won't help you much. Why? No. Why 11? I thought 10 means sometimes students say, oh, so early. I mean, I don't know, 10 o'clock is so early. No, I'm not getting 10 to 11. You want to move to 10 to 11, is it? Huh? He? Oh, you have another test at 10 to 11. Yeah. If you want to join, you can come back here, take it. If you come late because of this, I'll give you extra time. Let's say you come here at 11:15. Okay, I can give you extra time. The test is 45 minutes duration, but most of the time students finish within 20-30 minutes because it's MCQ. Because some questions, if you know it, you do it within seconds. You don't know it also, you have to do within seconds, no other way. Okay. So maybe some may need some calculation. I can send you later some sample questions. Okay. Some may need some calculations, may take time, but usually on the average, many students finish within 30 minutes. Okay. Um, then, okay, very soon, next few days, I will post the lab problem as well as some material, supporting material for the lab. So uh, the lab is going to be on socket programming. Okay, so basically you are going to use socket programming to transmit or send a file from one system to another system. Okay, very simple. It's not a difficult one. I understand it's an introductory level course for you. And also you are going to implement a variant of maybe stop and wait. I'm not going to give you sliding window and all. Some time back, I remember I gave maybe students made it more complex and other things. So you are going to implement on top of it, maybe on top of UDP or TCP, I'm yet to decide, some the stop and wait based protocol to transfer from one place to another place. And also I will ask you to measure the performance. Let's say, for example, okay, you increase the size of the frame and see whether it affects the transfer time, how much time it takes to transfer, what is the throughput you get and other things. I give you some example programs, okay, but they are in the Linux or C based programs, okay. Uh, so if you go through the example programs, okay, and also go through any textbook, a lot of material examples are available in the web, you will understand how the basic things works. I don't think you need much guidance on that, but still we conduct the first lab session is going to be in week 9. Okay, I'll send you the schedule. Okay, I will schedule the lab session on 4 days. Um, because Wednesday I cannot schedule because Wednesday you have the same lecture here, right? 11 o'clock. So Monday, Tuesday, Thursday, Friday, I will schedule lab sessions, and each one of you can go to 1 or 2 lab sessions. At least one lab session, we take attendance. We expect you to attend at least one lab session. So you go and try those example programs. You try yourself, make sure that it runs, and play with that. Okay, if you can understand the example programs, it would be easy to develop or to the assignment solution. For me, maybe 1 day is enough to complete. It depends on how much effort you put. Okay, or within few days you can finish. But still, I give you 4 weeks time. The demo is going to be in week 13. I give you 4 weeks time because sometimes you need some time to better understand the TCP or UDP. You know the stop and wait and other things, the concept of throughput, transfer time, okay. But how you can measure the time, what kind of uh, programming functions you can use, that is there in the example program, okay. Similar way you can do, okay. So basically you can use my example programs on top of it, okay. You can add some extra functions to solve the assignment problem. I can provide you some material or some uh, the presentation to explain like basic concepts in the how the example programs work and all. We have done this after the test before last year. Maybe instead of repeating it, maybe I can link it the same thing to you, or you can watch, okay, and you try to understand, okay, if you have any difficulty in working with examples, okay. And attendance is important for you there because you have a chance to interact with us to the graduate assistant to get the maximum help possible, because they may not be able to help you in solving the assignment problem directly, okay. Of course, to some extent they will get, but not line by line. They will not be able to help you. They will not, okay, because we want you to independently work. Is that fine? And again, the lab carries 20 marks. Don't take it light. It's easy component to score high marks, okay. So if you lose marks in the lab, that means you will be behind many others because they easily score. Several people score full marks also, 20 out of 20, if it works fine, okay. So very important, make use of this time. Week 13 will be the assessment week. You will be given maybe 15 minutes time for the demo. Then after your demo, you can leave. You can show demo. You will be also required to submit a report, but report is not graded in the sense that we are not going to look into in the English or presentation of your report. The report is basically help you to during the demo, okay, because all the performance, how much throughput you got for this particular packet size, this, okay, and those performance figures or data, you will plot it in your report and you can bring it to us at the time of demo, because at the time of demo you cannot run your program many times, okay, with 100 byte 500 byte frames, 1000 byte frame, okay, you cannot show all those things. And also the throughput which you get will be different from day to day, time to time, okay. Now you run your protocol, your solution program, the throughput may be X, but after 1 hour you run maybe different. Immediately you run this, it could be slightly different or significantly different also, okay. So what I would suggest is you run the program maybe few times, take the average throughput and plot it, okay. And what is important to note is the performance trend. If you increase your let's say frame size 100 bytes, 500 bytes, 1000 bytes, let's say you go up to 1500 bytes, what kind of trend you observe, whether the throughput increases or decreases, okay. If let's say there is an error, okay, whether there's what's the effect on this, etc. That is very important. In terms of absolute value, somebody may get throughput, let's say 100, somebody may get 120, doesn't matter, because they take readings at different times. Is that okay? We are not looking into, but if something goes wrong, we can see whether it's significantly, very significantly different than something is going wrong. But slight differences will be there between the students. It's an individual one, so don't try to copy from others. It is a very serious offense, okay? don't get into any problem. You try yourself. It's not a difficult one, okay? So although we do it in the Linux platform, I'll provide the lab account, everything, okay? Uh, if you want to do maybe in Windows or other things, other platforms, Java based or this, you are free to do so. I'm more interested in the solution, okay? But I provide you example in Linux or C, maybe C or C++ could help easily. Uh, but I'm not going to force you. Is that fine? Okay. So later you'll receive your login account and these things, password, everything you can, and also I will give you uh, the programs. Any questions on the lab part? Okay. I know that you may not be able to attend the assigned slot. Let's say you are given Monday slot, okay, morning 9 to 12. You may not be free. It does not matter, okay. If you are not free on that day, you join the other one. If you have valid reason, don't everybody. If everybody pushes to Thursday, Friday, then we overcrowded. There may not be any systems available. Okay, is that okay? And at least one day, at least for 2 hours, I want your attendance. I know sometimes out of 3 hours you may have one lecture. 11 to 12 you may have lecture, but 9 to 11 you may be free. So you can be there in the lab 9 to 11. Should be fine. Okay. And another interesting thing is that the same programs you don't need to go to the lab and run. You can run on your own computers, because there is a server, client, sender, receiver. Okay. Maybe server is the sender, maybe client is the receiver. So you can run on two different windows in your within your system. So you can develop your solution in your own computer. It should work. It should work. So to test whether it works correctly or not, okay, you can do that. But in terms of throughput and all, the values which you get within the computer will be very high, because there's no bottleneck. Am I right? So the throughput to get the actual performance reading, you should do it on two different systems. Better you go to the lab, okay, you run, let's say server here, client there, then take the readings. Okay. If you take the readings by running within your own single computer, it will be very, very fast. The throughput will be very, very high. Okay. Is that fine? Don't do that. But you can develop and test it within your computer. Finally, you can go there, spend some time to take the readings. That's all. Okay. That's all. So we'll see you on Wednesday.